Space is big, but it's peanuts compared to the eternally inflating multiverse. But just how many bubble universes does the eternally inflating multiverse contain? What are they like? And most importantly, what can they tell us about aliens? Imagine it. The observable part of our universe is 93 billion light years across, and that's just a small fraction of the stuff created in our Big Bang. But in the eternal inflation picture, ours is just one among uncountable bubble universes, bubbles that are continuously appearing and growing within a vastly larger space-time that itself expands at an exponentially accelerating rate. A greater inflationary space-time whose expansion never ends. We looked at the bizarre idea of eternal inflation in recent episodes, but we stopped short of exploring the full implications of this proposition. Those implications are, frankly, completely nuts. Some may also be true. Here's the scenario. The default state of the greater universe or multiverse is to expand exponentially due to the vacuum of space itself having a large and constant energy density. Energy locked into something called the inflaton field. Within that inflating space, tiny patches stop inflating. The inflaton field in that patch loses its energy, and so accelerating expansion stops there. Within each bubble, we get a new Big Bang that kicks off a more slowly expanding universe. But that bubble has an edge, and the edge spreads into the surrounding inflating space-time at the speed of light, causing inflation to stop within the growing bubble. If lots of bubbles form, they could collide with each other to produce a connected network of non-inflating universe. But the little patches where inflation persists are expanding so fast that they quickly dominate the non-inflating network of bubbles, and so the cycle of inflation continues eternally. Some questions spring to mind. Besides, what? For example, how many bubble universes can be made this way? How often do they collide? Are those universes similar to each other or wildly different? I'll give you an idea of our best thinking for all of these. Let's start with the first two, because these are basically the answers to our recent challenge question. Now, to fully answer these, we would need to know the true physics of the inflaton field, but we can figure some stuff out just based on the exponential nature of expansion. For example, in the challenge question, I asked you to calculate the relative number of new bubble universes that formed in 1 second compared to in the previous second. We assume that there's a fixed but unknown probability that a bubble universe will form in any given volume of inflating space. That means the number of bubbles forming at each point in time should be proportional to the volume of the inflating universe at that time. So, the rate at which that volume is increasing is the same as the rate at which bubble universes multiply. We assumed the minimum inflation rate that we think was needed to kick off our own universe. The scale factor, or radius of the universe, increased by a factor of at least 10 to the power of 26 in less than 10 to the power of negative 32 seconds. So, how much did the volume increase over 1 full second at that rate? Well, a scale factor or radius increase of 10 to the power of 26 means a volume increase of that cubed, so 10 to the power of 78. Every 10 to the power of negative 32 seconds, 1 cubic meter of volume becomes 10 to the 78 cubic meters, which is approximately the volume of our entire universe. And then in the next 10 to the negative 32 seconds, each of those 10 to the 78 new 1 meter cubes spawns just as many new entire universe-sized volumes. So we have 10 to the 78 squared, then 10 to the 78 cubed, etc. By the time we get to 1 full second, we've multiplied by 10 to the 78, 10 to the 32 times. So our volume is 10 to the 78 to the power of 10 to the 32, or around 10 to the 10 to the 34. And our number of new bubble universes should multiply by that same insane factor each second. This gives us a ridiculously large number of universes, even if the probability of making one universe per unit volume is insanely low. The exponential nature of expansion guarantees this. As soon as the inflating spacetime is big enough to make one universe, in the next second it should make 10 to the power of 10 to the power of 34 universes, and so on. If you got this right, congrats. We'll list the winners as well as answer the extra credit question at the end of this video, after the bit about the aliens. As crazy as eternal inflation sounds, it's still fun to think about the consequences if all of this is true. Here's another one. Do all of these bubble universes have the same laws of physics? Or could they be wildly different from each other? Based on standard ideas, they probably have the same number of dimensions as ours, 3 space, 1 time, but their contents and their physics could be very different. For example, the cosmological constant, the strength of dark energy, could be very different. Remember that it was the high energy density of the inflaton field that drove inflation, and the loss of that energy density that ended inflation. But what if the inflaton field retained just a tiny bit of energy after its decay? That residual field might be what we observe as dark energy. It's an open and contentious question as to why the current energy density of the vacuum should be so low without being exactly zero, given that it started out so large. It seems awfully lucky. If dark energy were much stronger, then our universe would have restarted its accelerating expansion too quickly for stars and galaxies and life to ever form. Here's a possible explanation. What if different bubble universes can end up with different vacuum energies? Very low vacuum energies like ours might be extremely rare, but there are so many bubble universes that at least some of them will have low enough cosmological constants for life to form. Naturally, we would be in such a universe. This is an example of using the anthropic principle. We must exist in a universe capable of producing us, so if there are many universes, it's natural we find ourselves in one finely tuned for life. People have also invoked the anthropic principle plus eternal inflation to explain a conundrum in string theory. As we've talked about before, modern string theory is difficult to pin down because there are countless possible minimum energy configurations of its 6 curled up dimensions. More than 10 to the power of 500 possible vacuum states. Probably a lot more than that. The vast space of possible configurations of these compact dimensions is referred to as the string landscape. Each different configuration results in a different family of particles and also a different cosmological constant. We don't know why our universe has the particular string vacuum state that it does, but it's lucky it does because the resulting particles allow for things like complex chemistry. Enter the anthropic principle once again. Eternal inflation gives us enough universes to easily populate the entire string landscape. All different vacuum states exist somewhere out there, and our universe necessarily has one that leads to life-friendly particles, as well as a decent cosmological constant. Some people aren't comfortable with the anthropic principle. Those people will be even less comfortable with the next idea. This one is from Alan Guth, the guy who actually invented inflation in the first place. Here it is. Eternal inflation may solve the Fermi paradox. It may explain why we don't see aliens. The argument goes like this. If the number of new universes increases by a factor of some impossibly large number every second, then the vast majority of universes in existence were born recently. There are vastly more universes born 1 second after ours than were born at the same second as ours. Now, imagine that there's a set amount of time for the first intelligent life to form in any one of these universes. Let's say 10 billion years. Pretend that it's the same in all universes down to the second. Now, the real timescale is going to be much more fuzzy than that, but it actually doesn't really matter for this argument. So, the first intelligence appears in our universe after exactly 10 billion years. We'll call that moment second 1. The same happens in the exact same second for universes that formed at the same time as ours. Now, 1 second later, second 2, you might get some more intelligent life forms forming in those same universes, maybe just as many as formed in second 1. But consider the wave of universes that formed 1 second after our own. These are now only just reaching that 10 billion year mark and producing their first intelligent life forms. And of course, there are vastly more of those slightly younger universes, more than all of the atoms in all of the universes that formed 1 second earlier. So, first civilizations in those younger universes will always outnumber the civilizations in older universes. The result is that at any one moment, almost all of the intelligent beings in the eternally inflating multiverse are in the youngest universes that have had time to form intelligent life. So if we imagine that we are a typical intelligent life form, then we're most likely the most common type across the multiverse, which means we're the first to appear in our universe. Ergo, you shouldn't be surprised that we don't see aliens. Guth calls this argument the youngness paradox. Now, let's be clear, he doesn't necessarily believe it to be right. He admits that while it seems logically sound, it does seem weird enough to force us to question the premises. He proposes that there may be something off in the logic of weighing up probabilities over bubble universes. On the other hand, he also doesn't rule this argument out. Okay, the last thing I want to talk about is colliding universes. How often does this happen? Let's start by answering the extra credit question. How close do bubbles need to be in order to collide? I won't go through the detailed calculation because it takes a wee bit of calculus. Instead, I'll provide a link to the answer in the description. But the too long didn't calculate is this. Remember that the edges of bubble universes expand at the speed of light. If they form too far apart, then the intervening inflating spacetime will throw them apart faster than light speed before they can merge. Assuming the crazy rate of inflation in the question, you get that two bubble edges need to be closer than 6 by 10 to the power of negative 50 meters in order to reach each other. This is something like 15 orders of magnitude smaller than the Planck length. The implication is that universes don't collide very often unless their rate of production is extremely high. And it might be very high, especially if the inflaton field is highly correlated from one point to the next, as in slow roll inflation. But it still should not be surprising that we don't see any evidence of bubble collisions in our observable universe. If such collisions happened, they're probably too far away for us to see. Okay, so we've come up with a lot of ridiculously large and small numbers, and convincingly shown that none of this is easily testable. Where does that leave eternal inflation? Well, we probably shouldn't just accept it, but at the same time, the current lack of proof doesn't mean it's wrong, just that the universe, or multiverse, is playing hard to get. But here's something that's not hard to get. Space-time swag. If your name is listed below, you are a winner of the challenge question and you get your pick of a swag item from our merch store. Email us your choice, any relevant size info, and your mailing address, and we'll get it out to you. Of course, you can always reward yourself for just listening to this answer by buying your own swag. A link in the description. It's the best humorous science apparel in all of space-time. Did you get enough space-time today? No? Need more of that existential awe at the wonder and weirdness of the universe? Got burning questions about the nature of reality? I may have what you need. We just launched a Spacetime Discord for 24/7 conversations on all of the above. Now, it's for our Patreon members, but don't worry, it's for the lowest of the lowest tiers, only $2 a month, to help support the show and to indulge that voracious curiosity of yours. I hope to see you over there. And on the subject of Patreon, I wanted to give a big thanks to Alexander Tomas, one of our Big Bang supporters. Now, Alexander has been traveling the bubble universes for many years, supporting local YouTube space shows where he finds them. Alexander, we're glad you found us, and safe travels wherever they may lead. Now, last time we visited that old argument, is Pluto a planet? The question gets to the heart of what a scientific definition really is. And a number of you found that the International Astronomy Union's new definition of planet, the one that excluded Pluto, is not very scientific at all. I thought it worth focusing on that for this comment response. A number of people in the comment section echoed these thoughts, but special props to Regolith on the Spacetime Discord, who's a bona fide planetary scientist. I'm also echoing some of the thoughts of Alan Stern, lead scientist on the New Horizons mission to Pluto. Now, there are two main arguments. Firstly, that the IAU definition is arbitrary and ambiguous. And second, that it should have been planetary scientists that made this decision, not astronomers. I acknowledged the arbitrariness in the episode, but ambiguity is more of a concern. That's something a scientific definition should never be. Here's the IAU definition again. A planet is a sun-orbiting body massive enough to be round and to have cleared its orbit of debris. It's that last bit, cleared its orbit, that excludes Pluto. This might be considered arbitrary because clearing the orbit doesn't necessarily reflect a fundamental difference in the physical nature and formation process of that body. And that's a problem for many planetary scientists. In fact, whether or not a body clears its orbit depends strongly on where in the solar system it forms. The further out, the more massive a body needs to be to clear its orbit. If Earth formed at 100 times its current distance from the Sun, it wouldn't have cleared its orbit, and so it wouldn't be considered a planet. But if Jupiter was in the same location, 100 times Earth's orbit, it would have cleared its orbit. So we end up with this somewhat complicated relationship between mass and the distance of the Sun that determines whether you get to be called a planet. And that relationship may not relate to any scientifically interesting properties of the body. So, there's your arbitrariness. But what about ambiguity? Within our solar system, it's clear enough which are planets and which aren't by this definition. But what about around other stars? That brings us to the first part of the IAU definition. A planet has to be orbiting our Sun. That's right, other stars don't have planets. They have exoplanets. The word planet is reserved exclusively for the 8 bodies of our solar system. In fact, you need this combination of requirements to know absolutely whether something is a planet by this new definition. In general, the new definition of planet does avoid ambiguity, but at the cost of arbitrariness. And you might also say, of scientific usefulness. Pluto aside, the new definition allows for 2 objects with extremely similar geophysical properties to be differently classed. For now, the new definition does make things clearer than they were before the definition was changed, but as our understanding grows, particularly of exoplanets, maybe we need to be very ready to change the definition again, and perhaps this time with more input from planetary scientists, who, after all, are the literal experts on planets and the most frequent users of the term.